Hypothalamus Artificial Intelligence, HI, and Research Center for Advanced Decision Technologies, RCADT, presents the conference. Distributed Kalman Filter and Image Data Reconciliation. Earth observation satellites are Earth-orbiting spacecraft with sensors used to collect imagery and measurements of the surface of the Earth. These satellites are used to monitor short-term weather, long-term climate change, natural disasters. Earth observation satellites provide information for research subjects that benefit from looking at Earth's surface from above, such as meteorology, oceanography, terrestrial ecology, glaciology, atmospheric science, hydrology, geology, and many more. Types of sensors on these satellites include passive and active remote sensors. Sensors on Earth observation satellites often take measurements of emitted energy over some portion of the electromagnetic spectrum, e.g., UV, visible, infrared, microwave, or radio. The Earth observation satellites classified in two large groups: satellites operated by government agencies of one or more countries, public domain, versus commercial satellites built and maintained by companies, private domain. Satellites can be classified by their function since they are launched into space to do a specific job. The satellite must be designed specifically to fulfill its role. There are different types of satellites: i.e. communications satellite, remote sensing satellite, navigation satellite, geocentric orbit type satellites, LEO, MEO, HEO, global positioning system, GPS geostationary satellites, GEOS drone satellite, ground satellite, polar satellite, nanosatellites, cube satellites and small satellites. The images obtained from multiple satellite systems used to observe geo-referenced variables in a specific area of the Earth. The proposed system is not limited to satellites. Parallel and distributed predictive analytics. Reference: satellite image processing. When analytics considers a single mathematical model that is solved by an integrated algorithm, which runs synchronously on a single computer, it can be called monolithic analytics, which most of its functionalities in a single process. For a large-scale system, it is necessary to design a superalgorithm that solves the data processing requirements in an integrated way and produces the desired results in a single pass. The drawback of this approach appears when the size of the application increases and needs to be scaled. To scale the application, the software team can design the application in the form of multiple distributed processes, microservices, that are integrated from the bottom up. The alternative, taking a monolithic process and breaking it down from the top down, although viable, is a tortuous path. Microservices are an organization of independent programs, algorithms, and other actions, which act in a small, well-understood context, and can work independently and quickly. This shortens the time of application development and the execution of parallelizable mathematical processes. One of the reasons for decoupling a mathematical model is directly related to the possibility of parallelizing it in such a way as to take advantage of modern computational architecture based on many multiple processors that allow the implementation of high-level parallel mathematical algorithms. State estimation, SE, is supported on a conception of the stochastic processes, where the random variables are clearly differentiated of their measures, being understood that the modeler has data of the measurement system that may be different from real values of the random variables. This differentiation is essential to understand the operation of the physical and measurement systems used for the observation of the physical system. The expert must define the differential equations that govern the physical system, and the data scientist must determine the system of measurement and its processing. The problem of reconciliation, or fusion, of satellite images is generated when the interested user has available S images from S sensors located in one or more remote measurement systems, satellites, each of them with their own characteristics. Each image is associated with a geo-reference variable and contains data which belongs to the real numbers. The process to follow is: at one or multiple times, each satellite in the network produces an image, with certain technical characteristics. All images must enter in a reconciliation process, and thus the reconciled image is obtained, which must be in accordance with what the user wants. The problem of image reconciliation does not have a single solution, a revealed truth, It depends on the modeler who chooses the model to use. Since, as in any process associated with highly complex mathematical modeling, there will be a compromise between multiple criteria that intervene when deciding which is the best solution. I. The accuracy of the models. 2. The solution time. 3. The required databases. 4. The knowledge included in the solution. V. Implementation time. Vi. Flexibility of maintenance. The resources, costs, used are criteria that move in opposite directions. Therefore, the IT solution to be implemented is a mixture of art and high-level science. The first step to carry out the reconciliation process of multiple satellite images is to define a universal grid in the 2D spacetime in which the information of all the satellite images involved in the process will be integrated. The cells of the grid, the original of the image and the universal, are associated with the coordinate of the cell's centroid. Each image from a satellite is converted into pixels and must be in an area of the Earth it covers. This area can be very large or very small. These areas can overlap, so it is necessary to weigh the information received to select a reconciled value. The opposite is the case of areas without coverage, where it is necessary to extrapolate their values from other known data. Dynamically positioned satellite imagery moves permanently, and in the same way the reconciliation process must follow its movement. Statically positioned satellite imagery does not move, and the reconciliation process is not necessary as the measurement is always located over the same area. Satellite images must be transformed into homogeneous matrices to facilitate the process. This may not be easy when the meshes of the images cannot be uniformed in spacetime. The reconciliation process will have some original variables, those that come from the original instruments, and an output variable in which the new images will be generated. To achieve this union, a process of transformation is required, if there is no uniformity between the input and output. The process involves a Kalman filter for the original images, which will produce the filtered input for the transformation process. Kalman's filtering process uniformizes the matrices of the variables before and after the filter. If there is variable matching, the filter must standardize the arrays according to the variable type. Nowadays, a network of satellite systems is a complex system that is difficult to process. Each satellite, and there are quantities, produces a series of satellite images. Satellite produces information about two variables: infrared rays and water vapor. In this case, from the observations, synthetic images are produced based on mathematical models, to improve the measurements. Models are also used to project the future. The image shows the map of global salinity built from several satellites. A swarm of dynamic signal meters gives rise to the distributed Kalman filter, DKF. The continuing trend toward connected sensors, Internet of Things and ubiquitous computing, drives a demand for powerful distributed estimation methodologies. In tracking applications, DKF provides an optimal solution under the conditions of the Kalman filter. The optimal solution in terms of estimation accuracy is also achieved by a centralized fusion algorithm, which receives all associated measurements. The centralized approach requires complete communication of all measurements at each step, while the DKF operates at arbitrary communication speeds as the calculation is fully distributed. The efforts developed by distributed Kalman filtering, DKF, began with the work of Romeliadis and Becky in the year 200, who decentralized the Kalman filter for linear propagation of states and linear measurement equations. One example is a swarm of drones working together as a unified and coordinated system to achieve a common goal. Drones communicate with each other or, through a central center, using artificial intelligence to make collective decisions with minimal human intervention. Consensus-based Kalman filters. Distributed sensor fusion in sensor networks is one of the most recent applications of consensus problems. It is done by applying different problems that require implementing a KF called average consensus problems. It should be noted that there is more than one way to perform information fusion, which is part of the design of the distributed processing system. Efforts to decentralize the Kalman filter were initiated with the work of Romeliadis and Becky, 2002. They decentralized the discrete time Kalman filter for linearized state propagation and measurement equations. Let's consider an estate estimation problem with multiple system of sensors which are connected through a communication network. If all measurements are delivered to one place called fusion center and processed together, the process is called centralized Kalman filtering, CKF. When there is no fusion center, each system of sensor can also solve the problem by using local measurements and exchanging information with its neighboring sensors, which is called distributed Kalman filtering, DKF. Noting that CKF problem is a maximum likelihood estimation problem, which is a quadratic optimization problem. DKF reformulates the problem as a consensus optimization problem, resulting in that DKF problem can be solved by many existing distributed optimization algorithms. In addition to sensor networks, distributed filtering can benefit several other applications such as formation flight of aerial vehicles, cooperative robotics, and disciplines related to global navigation satellite systems, GNSS. Communications network topology. The way a sensor node transmits information to other nodes defines the interaction topology between nodes. It is often described by a directed graph whose vertices and edges represent the nodes and communication links. Consensus problems are widely considered in computer science. Consensus filters are the formulation and classification of different available filters and their equations. They were introduced in the 60s in the field of distributed computing, by researchers working in management science and statistics. De Groot's notion of consensus statistical theory attracted interest 20 years later, in the problem of processing information with uncertainty obtained from multiple sensors and medical experts. It is worth noting the article Assessing Radar Performance Without a Gold Standard Using Consensus Theory by Weller and Mann in 1997. Distributed computing has been considered in systems and control theory as an asymptotic asynchronous agreement problem for distributed decision-making systems. Considering that there are multiple alternatives to implement a CKF, the methodology proposed by Gavers, distributed Kalman filter, in the book Kalman Filters, Theory for Advanced Applications, has been taken as a reference. A distributed Kalman filter, DKF, is an estimation algorithm that allows a network of sensors to cooperate to estimate the state of a dynamic system without relying on a central processing unit. Unlike centralized methods, where all data is sent to a single place, in DKF each node processes its own local measurements, and exchanges information with its direct neighbors to reach a consensus on the overall state of the system. The operation of a DKF is generally based on the integration of local filters and network communication strategies. The main components are micro-Kalman nodes. Each sensor runs a shrunken, local version of the Kalman filter to generate a preliminary estimate based on its own data. Consensus filters, communication algorithms that allow nodes to agree on information matrices through repeated interactions with their neighbors, and information representation. Many DKFs use the Kalman filter information form, based on the inverse of the covariance matrix, since information contributions from multiple sensors can be easily added together in a distributed manner. The image shows three different interpretations of the land map of Ireland. The graph presents an example based on a convex combination of multiple Kalman filters. The process involves implementing a KF on each sensor node and then generating a filter consensus using covariances weights on each node that is part of the consensus. DKF has been applied to a network of receivers tracking global navigation satellite systems, GNSS. This is relevant to the Satellite Imagery Reconciliation Project. It is the conceptual basis used for the integration of the information processed in each sensor node. The complete process of the formulas proposed by Gavers can be found in the original paper. Below is the summary of these formulas to be considered by the data scientist responsible for the implementation of the Fusion Center. Groups of sensor nodes may form according with the topology of the network. The nodes can be fixed, as would be the case with a wind turbine farm. The nodes can be mobile, in time and space, as is the case with drones, whose position can change according to needs. This fusion process can be performed with any sensor mix. For example, 3 types of measurements are integrated into this system to improve the image of a region of the Earth. An equipment, such a wind generator, an airplane with its own images, and a satellite. Multiple measurement systems of the same object offer the integrated observer a view from multiple perceptions of spacetime. The graph summarizes the flow of the proposed design for reconciliation of satellite images. Distributed analytics for image reconciliation. The following summarizes the proposed design for the implementation of a distributed system of predictive analytics algorithms to face the problem of image reconciliation. Each sensor node included in the measurement system produces information asynchronously, over time and space, for a group of geo-referenced variables dependent on each sensor node. When the sensor node information is obtained, it is possible to carry out an autonomous and independent process of state estimation of the variables measured. The result is a collection of matrices in 2 dimensions for the variables measured and its first statistical moments, mean and cross-covariance. This information is stored in a knowledge database. To implement the KFs for each node sensor, the modified state estimation framework for 2D images must be used. Depending on the size of the images and the processing required, it is suggested to consider image processing with line image processing as a reference, called Kalman strip filter, KSF. This implementation is aimed at online image processing, but it can be used for offline processing. The methodologies used in the processing of data from each satellite may be completely independent of the processing on the other sensor node and may, or may not, make use of the distributed analytics approach. For each sensor node, the algorithms to be implemented can depend on each specific case. In this case, it is recommended the Kalman filter, KF, considering variations oriented to the estimation of the matrices that characterize the first 2 moments of the probability distribution of the state variables. At a certain moment, of the day, week, month, the user requires official information for a group of variables from a sensor node group. This implies the reconciliation of information on several sensor nodes. At that point, a top-level algorithm, a fusion center, must be activated to produce the reconciled image, from the images the group, or from a selected sensor in the group, for a geo-referenced variable, and for the process of merging images, it is proposed to use the so-called distributed Kalman consensus. Global Navigation Satellite Systems, GNSS, have been shown to be an efficient tool for determining time-varying parameters, and that they are important for earth science disciplines such as positioning, deformation, atmospheric variables, and others. GNSS parameter estimation is based on data processing from a network of receivers that collect measurements from visible GNSS satellites. They function as sensor nodes, providing their data to a fusion center, calculating network-based parameter solutions in near real time. Kodabande et al. Simulate a network of 13 GNSS receivers located in Perth, Western Australia, each receiver having data links, red lines, to its neighbors with interstation distances up to 4 kilometers. Math modeling for a network of GNSS receivers tracking GNSS satellites. The way in which nodes interact with each other to transfer information is called interaction topology. It is described by a directed graph whose vertices and edges represent the nodes and communication links. This peer-to-peer distributed estimation method gives a distributed Kalman filter algorithms with many different consensus strategies. The figure represents a network of 20 nodes with their 2-way static communications links. The number of links between nodes can vary depending on the session. Each session represents a graph that may not be connected. In a connected graph, each node is linked to all the others at least through one path. The figure shows an example of the sensor fusion process, where the covariance of the position between satellite number 1 and the client spacecraft can be improved by merging the data from all the spacecraft in the swarm, even considering the GPS position errors, which define the location of each spacecraft with respect to satellite number 1. More details on the algorithmic steps of the CKF in the original article. While satellites revolve around the Earth, not all of them are visible simultaneously to the small-scale regional network. For example, in the case of the city of Perth, Western Australia, the visibility of 32 satellites over time is shown in the left panel of the figure. The right panel shows the trajectories of the ionospheric pierce points in the single ionospheric layer that are formed by line-of-sight paths between the receiver and the satellite. Standard deviation of the central, green, and local, red, of solutions of the TEC parameters. According to the results in the figure, central TEC solutions significantly outperform their local counterparts in the sense of delivering more accurate results, such as local central standard deviation ratios being considerably greater than 1. The figure presented with the proportions indicated corresponds to two different data submission rates, 15 and 5 seconds, left and right panels. In both cases, the CKF to central standard deviation ratios are lower than their local central versions, illustrating that employing CKF effectively improves the accuracy of local solutions. In communications lasting 5 seconds, the corresponding ratios are very close to 1. In that case, the CKF of each receiver is expected to have a similar accuracy performance as the central filter. However, for the 15 seconds case, the CKF performance of each receiver is highly dependent on the number of neighbors of the receiver. Modern analytics can be divided into two: monolithic, or distributed. Industry 4.0 indicates that, from now on, distributed analytics will take the lead. Now with the advent of Industry 6.0, the new way of mathematics is directly related to the parallel thinking, and today it can be said that like paper-based math, sequential mathematics for single-processor computers, will be in the short term a dead language. As in the human brain, in the future only parallel mathematical thinking will be practical. The new analytics is autonomous, parallel, and distributed. Tribute to Hernando Duran Castro, my master's professor, in 1975, at the Universidad de los Andes. Nothing is necessary, nothing is enough, everything is useful. Always must learn. I add it. May he rest in peace. Thank you for your attention.